You're standing in the painted desert of Arizona. Red sandstone stretches to the horizon. The air is dry, sharp, still. Now dig down through those rocks, through layers of rust-colored stone laid down grain by grain in an ancient wasteland. And you'll hit something strange. A band of black shale, dark, organic, waterlogged. Then below that, red sandstone again, just like the surface. That black layer is a scar. It marks the moment 234 million years ago when the driest parts of Earth became swamps for 2 million years straight. This is the story of how volcanic fissures rewrote the rules of climate, drowned an entire world, and accidentally handed the planet to the dinosaurs. 235 million years ago, Pangaea was a single landmass stretching from the North Pole to the South Pole. No Atlantic Ocean, no Pacific separating Asia from the Americas. Just one enormous continent surrounded by a single enormous ocean called Panthalassa, the interior of Pangaea, thousands of kilometers from any coastline, baked under relentless sun. There were no polar ice caps. Global temperatures ran several degrees hotter than today. Rain came in seasonal bursts called mega monsoons. But between those pulses, the land dried out completely. Rivers existed, but most were ephemeral. They swelled during the wet season and vanished during the dry. The landscape looked like modern Arizona or Central Australia. Red rock, scattered shrubs, occasional stands of trees near water. Deserts dominated everywhere. The flora had adapted accordingly. Seed ferns, extinct plants that produced seeds but resembled ferns, covered much of the undergrowth. Conifers, the ancestors of modern pines, formed forests where water persisted. Cycads, squat and palm-like with waxy leaves to minimize water loss, dotted the plains. The animals that thrived here were specialists perfectly adapted to this harsh world. Decinodonts, herbivores the size of cattle with barrel-shaped bodies, beaked snouts, and two prominent tusks were the most successful large plant eaters on the planet. Placerias, a North American species, traveled in herds and used its beak to slice through tough fibrous vegetation. Rhynchosaurs, smaller herbivores with powerful jaws and teeth fused directly to the bone, fed on roots and tubers. Etosaurs, four-legged, heavily armored archosaurs covered in bony plates, looked like armored pigs and browsed on low-growing plants. The apex predators were Rauisuchians. These were not dinosaurs, but a separate lineage of archosaurs that walked on four legs and could rear up on two. Postosuchus, built like a crocodile crossed with a tyrannosaur, hunted the herds of decinodonts. It was the top carnivore in a stable ecosystem that had persisted with variations for tens of millions of years. Dinosaurs existed, yes. They were small, bipedal, and rare. They left few fossils. They were nobodies in this world, dominated by others. Around 234 million years ago, the western edge of Pangaea, in a region that would eventually drift north to become Western Canada and Alaska, began to split open. Fissures hundreds of kilometers long opened in the crust. Magma welled up from the mantle and spread across the surface in floods of basaltic lava. In some places, the lava piled thousands of meters deep. The eruptions covered millions of square kilometers and continued on and off for hundreds of thousands of years. The lava itself was a local catastrophe, but the gases it released were a global one. Magma contains dissolved volatiles, primarily carbon dioxide and sulfur dioxide, that erupt explosively into the atmosphere when pressure drops. The Wrangell eruptions pumped billions of tons of CO2 into the air. Atmospheric CO2 concentrations, already higher than today, spiked even further. Carbon dioxide is a greenhouse gas. It allows visible light from the sun to pass through the atmosphere and warm the Earth's surface. When that surface tries to radiate heat back into space as infrared radiation, CO2 molecules absorb it and re-radiate it in all directions, including back toward the ground. This is the greenhouse effect. It's natural and necessary. Without it, Earth would be a frozen ball. But the Wrangell eruptions overloaded the system completely. Global temperatures rose by an estimated 4 to 7 degrees Celsius. That doesn't sound like much. It was enough to change everything. The oceans, which cover most of the planet's surface, began to heat up dramatically. Warmer water evaporates faster than cool water. The superheated surface of the Panthalassic Ocean started pumping water vapor into the atmosphere at an accelerating rate. Water vapor is itself a greenhouse gas. So this created a feedback loop. More heat, more evaporation, more heat. The atmosphere became saturated with moisture. The hydrological cycle, the movement of water from ocean to air to land and back, went into overdrive. All that water had to come back down somewhere. If you're finding this fascinating, subscribe now, because what happens next is one of the most dramatic transformations in Earth's history. The warming didn't happen overnight, but in geological terms, it was sudden. Within tens of thousands of years, the climate system of Pangaea began to shift fundamentally. The seasonal mega monsoons, which had been intense but predictable, started to change character. They became longer, heavier, more frequent. The dry seasons shortened, then they disappeared entirely. By around 234 million years ago, much of Pangaea had entered a new climate state. It rained, not in the sense of a single storm system, but as a persistent condition. The atmosphere held so much moisture that precipitation became near constant across vast regions. This was the Carnian Pluvial episode. The rain fell for 2 million years, not continuously at every location, but as a planetary climate regime. Instead of distinct wet and dry seasons, the world experienced wet seasons and wetter seasons. River systems that had been seasonal became permanent and powerful. Erosion accelerated dramatically. Sediment, sand, silt, clay washed off the land in torrents and poured into the surrounding ocean. The landscape began to drown. Red sandstone, the signature rock of arid environments, stopped forming. In its place, dark shales and siltstones accumulated in swamps and shallow lakes. Coal beds formed from the compressed remains of waterlogged plants and began to appear in the rock record. In the oceans, the influx of sediment was so massive that it choked out the carbonate platforms, the Triassic equivalent of coral reefs. These shallow water ecosystems, which had thrived by precipitating calcium carbonate from seawater, were buried under layers of mud. This shift is visible in the geological record on every continent. Below the Carnian Pluvial layers, red rocks, evaporate deposits, fossils of arid adapted life. Within those layers, black shales, coal, amber. Above them, red rocks again, but with a completely different cast of fossils. The CPE left a global scar in the Earth's crust that we can still read today. The transformation of the landscape was total and devastating. The deserts of Pangaea's interior became swamps. Ephemeral rivers became permanent waterways, carving deep channels through the bedrock. Floodplains expanded. Lakes formed in basins that had been dry for millions of years. The entire hydrological architecture of the continent changed beyond recognition. The fossil record shows this in fine detail through pollen analysis. The study of fossilized pollen grains preserved in rock reveals a dramatic shift in plant communities. Before the CPE, pollen from seed ferns dominates the samples. These were the plants of the arid world. As the rains began, their pollen disappeared. In its place, spores from ferns and pollen from conifers. Ferns thrive in wet environments. Conifers, with their deep root systems, could tolerate the waterlogged soils that were forming across the continent. The flora died first. Seed ferns, which had covered vast areas of Pangaea for tens of millions of years, were adapted to dry soils and seasonal water availability. The constant rain waterlogged the ground. Roots rotted. Seeds failed to germinate. Within a geologically short period, perhaps tens of thousands of years, seed fern communities collapsed across much of the continent. Conifers and ferns moved in to replace them. These plants had adaptations that allowed them to survive in wet conditions. For the herbivores that depended on that flora, this was a death sentence. Dicynodonts had evolved over millions of years to process tough fibrous plants like seed ferns. Their beaked jaws, powerful neck muscles, and specialized teeth were optimized for that specific diet. When the seed ferns disappeared, the dicynodonts had no fallback. They couldn't efficiently digest the new vegetation. Populations crashed. Within the CPE layers, dicynodont fossils become rare. By the end of the episode, they were functionally extinct in most regions. Rhynchosaurs suffered the same fate. Their fused teeth and jaw structure, perfect for slicing through roots and tubers, were useless in a world where those plants no longer grew. they went completely extinct. The collapse of the herbivore populations cascaded up the food chain. Rauisuchians, the apex predators, depended on herds of dicynodonts and other large herbivores for prey. When those herds vanished, Rauisuchian populations plummeted. They didn't go extinct immediately, but their dominance ended. The niches they had occupied for tens of millions of years were suddenly vacant. Carnivorous dinosaurs followed, with new herbivores to hunt. Theropods, the lineage that would later produce Tyrannosaurus and birds, diversified. They grew larger and more specialized, with the fossil record showing clear increases in size and ecological roles. Why dinosaurs? The debate continues, but several advantages stand out. Upright limbs made them energy efficient and fast. Rapid growth allowed them to reach maturity quickly. Their generalist diets and adaptability gave them an edge in a recovering world. The Carnian Pluvial episode lasted roughly 2 million years. Then it stopped. The Rangelia eruptions ended. CO2 levels stabilized. The greenhouse effect weakened. Rainfall decreased. The world dried out again. Not to the same degree as before, but enough that deserts returned to some regions. But the world those rains left behind was unrecognizable. The ecosystems that had dominated Pangaea for tens of millions of years were gone. In their place, dinosaurs. By the end of the Triassic, 30 million years after the CPE, dinosaurs were the dominant large animals on every continent. They would remain so for the next 150 million years. The CPE is a reminder that Earth's systems are interconnected. Volcanism affects the atmosphere. The atmosphere affects the oceans. The oceans affect rainfall. Rainfall affects ecosystems. Ecosystems affect evolution. A volcanic eruption in one region can, through a cascade of feedbacks, restructure life across the entire planet. The 2 million years of rain that drowned the old world created a new one. The dinosaurs didn't conquer the Earth. They inherited it by accident.